So far we talked about the directional derivative. Remember that we said that if function f has limit definition, so let's write down that limit definition, the directional derivative of function z equals to f of x and y at the point x sub 0, y sub 0 in the direction of vector, in the direction of unit vector u, which is defined as a and b, is defined as b of f x sub 0, y sub 0 in the direction of u. Limit, now limit definition f of x sub 0 plus at y sub 0 plus bt minus f of x sub 0 y sub 0 divided by t as t goes to 0. If this limit exists, then we say that we have this function has a derivative in the direction of this unit vector. And remember that if the limit definition exists, then we can rewrite this as the directional derivative of function f at the point x sub 0, y sub 0 equals to partial derivative of f with respect to x at point x sub 0, y sub 0 times a plus partial derivative of f with respect to y at x sub 0, y sub 0 times b. It happens that this guy has a definition. We can define the gradient vector, which is denoted by Nabla operator. The gradient of f is equal to, it's going to be a vector function, f of x, comma, f of y. Well, what I'm doing here, this is what's happening. I'm saying that, hey, I have the gradient of the function dot product with unit vector u. This is your dot product. Okay. So here you have the partial derivative of f with respect to x at the given point, x sub 0, y sub 0, and the partial derivative of f with respect to y at x sub 0, y sub 0, dot product with unit vector u, which is a and b. Remember the dot product, you're multiplying the first components, you're multiplying the second components, and add them together. This guy is equal to partial derivative of f with respect to x times a plus partial derivative of f with respect to y times b. So as you can see, we can rewrite the directional derivative using the gradient. So this I can written as directional derivative of f in the direction of unit vector. Guys, I'm emphasizing on unit vector. If it's not a unit vector, you have to make it to be a unit vector. X sub 0, y sub 0 equals to gradient of f dot u. Okay, so that's the definition of gradient. Let's go over one example for you. Question says, example, find the directional derivative of function f of x and y is defined to us as, let's take a look at note, x squared y cubed minus 4y at the point 2 and negative 1 in the direction of vector v, which is defined to us as 2 plus 5, 2i plus 5j, or 2 and 5. Okay. So it asks us to find the directional derivative. We're looking at the definition. We know that, hey, we need to have a unit vector. You need to check to see if this guy is a unit vector or not. Note that. Important note. Let's use a different color. V is not a unit vector. Why? What's the reason? Because its magnitude is not 1. The magnitude of vector V is equal to square root of 4 plus 25, which is equal to square root of 29, and it's not 1, right? So it's not a unit vector. So what should I do? Should I stop here? No, you can make this guy to be a unit vector. So we make this into a unit vector. How? Divide vector V by its magnitude. Vector U, unit vector U is equal to vector V divided by its magnitude. Well, the very first component is 2, so 2 divided by square root of 29, and the second component is 5 over square root of 29. Now we have a unit vector that we're going to use. So the gradient of this, we can find the gradient and then use the directional derivative. The gradient of f is equal to partial derivative of f with respect to x and partial derivative of f with respect to y. The gradient of f is equal to partial derivative with respect to x is just 2x, y cubed, and this is going to be just 0, comma, with respect to y, we have 3x squared y squared minus 4. Very good. You can evaluate that at the given point 2 and negative 1. So the gradient of f at 2 and negative 1 is equal to, we have 2 times 2 times negative 1 and 3 times 2 squared, negative 1 squared minus 4. So the gradient of f at this point is equal to, so let's say we have negative 4. And let's see, here we have negative 12 minus 4, negative 16. Hope all is correct. The algebra is correct. Okay, let me see. Oh, this is positive. So it's going to be 12 minus 4, which is 8. Okay, I didn't see that 8. Cut it right here. So now that we have the gradient, you can follow the definition of the directional derivative of function f in the direction of unit vector u, which is going to be, well, just the dot product between these two guys. Okay, let me just use this here. So gradient of f dot u, which is the directional derivative of f in the direction of u, is equal to, here we have negative 4 and 8 dot product with 2 over square root of 29 and 5 over square root of 29. Here we go. So here we have negative 8 over square root of 29 plus 40 divided by square root of 29. And we get 32 over square root of 29. And if you need to use your calculator to get an approximation for this number, you can go ahead and use your calculator. Otherwise, you can just leave it as it is. So as you can see, the rate of change of the function in the direction of this vector is positive. So the rate of change is positive. It is increasing.